forgot to record actually. Yep. So what's your question?
Yeah, I was just wondering if we could at some point go over the Lagrange remainder rule again once more, just use.
Okay, sure. Yeah, I can do that. So Lagrange, let me make a list. I mean, in the order that you guys asked. I will find the corresponding question so that everyone can. Okay. So the first one is Lagrange remainder. Any topic you guys want me to go over in the second place? So maybe similarly here, there's alternating test, alternating estimate, series estimate. It's related to these. Okay. And a second question, I would say maybe I should go over actually the following one is testing testing convergence or convergence test. Okay, or divergence test. Yeah. And that includes absolute convergence, conditionally convergence, and divergence case. What else? Yes, the third one I definitely want to go over is different integration techniques. Okay, that's something that you must know actually. And also here you have the geometric theories, summation formula. Okay, and number 4, the inverse functions here. And number 5, finding limits using L'Hopital rule. L'Hopital rule. Limit. Number 6, I guess, is the tank problem. That's always going to be there. And tank problem, and then the application like volume, like lens, and also that's yeah. So basically, work volume, lens. I guess that's pretty much on the spring. I guess that's another question. Okay. Yeah, I think parameterized curve, and also here you have parameterized curve. Okay, anything that you guys think I have missed here in this list? So that's going to be roughly the order I'm going to review this exam actually. Okay, so without any further ado, let me actually begin with the last one, how to find the radius convergence and Lagrange remainder formula. Okay. So the first example I want to see is the following one. Is this one. So example 1 is this question here. Actually, let me find a good example here because I don't really have for Lagrange remainder estimate. So let me see. So the kind of question I want to see is the following, is this one actually. So first one is, given this summation, this series, this should be easy at this moment since you have just taken the exam 4 on this topic. My first question is kind of mixture of number 1, number 2. I want first to discuss if this one is converging absolutely, conditionally, or diverges, and also finding the sum of the series with the error less than 1/8. So it's actually related to the alternating series test. Okay. Find the smallest n so that error is smaller than 1/10. The second type of question is, suppose that fx equals to sine x. Find p3x and evaluate p3 2/3, and then find a upper bound of error in using p3 2/3 to estimate sine 2/3. Okay, so these are the two typical questions you have actually on the final on a question like these. Okay, let's do it actually together for both of these. So example 1 and 1 prime. Example 1 and 1 prime. So for number 1, the example 1, how do you actually determine the convergence divergence situation of this one? This is actually pretty easy, because you can see when you take the absolute value of the series becomes 2/n², which actually equals to 2 times summation n goes from 1 to infinity 1/n². And this is straightforward, right? This is a p series, which has p to be larger or equals to 2. So it's larger than 2. So in this case, actually, it's a p series with p equals to 2 larger than 1. So we know that the absolute value of the series actually is convergent, hence its absolute convergence. Of course, for the final exam, I guess the testing question will be definitely harder than these. It's not going to be a straightforward p series, but the general scheme or steps you'll be following will be the same, actually, to testing for absolute convergence. You look at the absolute value of the series to see if it's converging there. Okay. Once we know its absolute convergence, of course, it's going to be convergent on its own as a alternating series, because the nth term actually goes to 0 and it's decreasing to 0 as n becomes larger and larger. Okay, so that's another. That also means it's converging too. So on its own. So now the major question is, how do you make an estimate of this series by finding the smallest n so that the nth partial sum will be approximating the real sum with an error smaller than 1/10. Remember how I did this question is by making a list of the first few terms until I come with a term that is actually smaller than 1/10. Okay, so let's do that. So when n equals to 1, so let's see the summation here. The first term is when n equals to 1, and that corresponds to 2/1. Minus 2/2² is 2/4. The third term is a plus, is 2/9. And the next term is a 2/16. And the next term is plus 2/25. And you can see that this is the term which is smaller than 1/10, but this is actually larger than 1/10, right? This is 1/8. So n equals to 5 is actually the first time for which this term is actually smaller than 1/10. So that means the first of 4 terms added up together will be a good approximation to the alternating series with the error smaller than 2/25, which in turn is smaller than 1/10. Is our choice. And S4 that equals to 2 minus 1/2 plus 2/9 minus 1/8 is the approximation we need. So that's kind of the standard way to solve an alternating series test, is always writing out the first few terms explicitly until you run into a term that is smaller than the given bound you're looking for the error, okay? So this is the kind of alternating series. I believe that you guys definitely can solve this kind of question. So now let's look at the second example, which is a different type. Suppose you are given a function. This is generally what will be asked. You'll be asked to find the third Taylor polynomial of the given function or other degree Taylor polynomial of the given function, and evaluate the Taylor polynomial at a given point so that this will be considered as a good approximation to the original function's value at the given point. Okay, the reason why this is a good estimate is, remember, Taylor polynomial is generally considered as the best nth degree polynomial approximation to your given function. That means if you are among all the possible nth degree polynomial, in our case, the third degree polynomial, this is going to be the best approximation to the given function. So their values will be close to each other. So that's why we will be choosing this value, the Taylor polynomial, Taylor polynomial's value at 2/3 as approximation of sine 2/3 degree. Okay, that's kind of the idea behind the calculation. So now let's quickly do that. So what is sine 0 is 0. Sine prime, the first derivative is cosine, so f0. F prime 0 is cosine 0 equals to 1. And f double prime 0 is actually negative sign, so it's 0. And f triple prime actually equals to, I think it's minus cosine, so it's minus 1 in this case. So P3x in this case actually equals to x minus x cubed over 6, I believe. Okay, that's for sine. And also, of course, another way to find P3 is because we know for sine x, this actually equals to n goes from, depending on where you start, actually. Let me make it, let me find the power series sine. Generally, people use n equals to 0 to infinity. So this is the power series expansion of sine. Okay, as you can see, when you choose n equals to 0, that's why you get 2n plus 1. If you choose n equals to 1 as your initial term, this would be 2n minus 1. That's where I'm kind of not quite sure how to use. But anyway, so this means that it's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, blah, blah, blah. So the P3 will be exactly all the terms that has a degree less or equals to 3, which correspond to the first two terms. And hence you can find your P3 there, okay? So for this class, knowing the power series expansion for sine, cosine exponential function is a must. But since you guys have the textbook with you, I guess this won't be a problem for that, okay? So once we find P3 then the question is, you want to compute P3 over 2/3, which is by simply plugging 2/3 into the polynomial you just computed. So I won't be evaluating this explicitly, but at home, during the exam, you can definitely simplify this further so that it becomes a fraction, reduced fraction or something like that. That's definitely going to be needed. Okay, so today, but I'm omitting here the steps without finishing the answer here, but you see the idea. The key point for this question is to find the upper bound for the error if I'm going to use P3 2/3 to approximate sine 2/3. Okay, we know they are close to each other, but we want to find the upper bound for that. This is where the Lagrange remainder formula comes into the picture. And let me remind you again, what's the Lagrange remainder formula is that Rn is going to be equal to the max. Since we are evaluating at 2/3, this will be our A. And we have x to the A to the n plus 1 over n plus 1 factorial. Okay. What is the n here? N is a degree of Taylor polynomial we are using. So if we are taking P3 as our approximation, n will be 3 in our case. And sorry, I mean, there's something wrong here. Let me write on a different line, which is correct. This is f to the n plus 1's derivative x with absolute value times a to the n plus 1 over n plus 1's factorial. Okay. So this is all the terms that's involved in computing the upper bound. So remember that this will be a number, and it's the upper bound for the error estimate. Okay. So in our case, n equals to 3, a equals to 2 over 3, and what is f prime to the fourth power? F prime to the fourth power will be something like a cosine, but since we are taking absolute value, this will be a cosine x, I guess, right? With absolute value, okay? So in this case, R3 will be smaller equals to the max when x is varying between 0 and minus 2/3 to positive 2/3 for cosine x times 2/3 to the n plus 1 over n plus 1 factorial. So in this case, what is that? That is going to be 1, which is the upper bound for this expression, since it's a cosine function, times 2/3 to the fourth power over 4 factorial. Okay. Does this make sense to you guys? Why I'm choosing this to be 1, and why I'm taking a to be 2/3, and why I'm taking n to be 3? Because if you understand these 3 things, everything else is just straightforward plugging into the formula I have here. Okay. But for this question, there's a different way to do that, because instead of using the Lagrange remainder estimate, let me give you a sense what is sine 2/3. Sine 2/3, by the formula we have written before as a power series. Let me remind you what's the power series for that. As you can see from here, the power series for sine x is given by these. Hence, sine 2/3 equals to 3 to 2/3 minus 2/3 over 3 over 3 factorial plus 2/3 to the 5th over 5 factorial minus blah, blah, blah. Okay. What we are doing right now is we are using these 2 terms, which is the P3 2/3, as our approximation. Okay. If I'm doing that, can someone tell me, if I'm using the alternating series error estimate, what will be the upper bound for the error if I'm using P3 2/3 as the approximation here? So the error will be bounded by this term. That makes sense? Okay. So this actually will be giving me the bound for the error. So you can see here, instead of using the Lagrange remainder estimate, because the series here is actually alternating series, so I can also use alternating series upper bound, which is given by these. So what is that? That means the error here is actually smaller equals to 2/3 over 5 over 5 factorial. So if you look at these 2 different estimates, which one is better, you think? If I'm using the Lagrange remainder estimate, I get an upper bound, which behaves like 2/3 to the 4th power over 4 factorial. But we also know the error is smaller than these by the alternating series test. And the bound is actually becoming smaller. You can see, right? So that means on the exam, if there's no specification which estimate you must be using, if the given series is actually an alternating series, you can use either one to produce the error bound that is required. That makes sense? Is this clear to you guys? If the question specifies explicitly, you need to use the Lagrange remainder estimate, then you do the previous computation. But if there's no requirement as to which estimate you want to use, you can use either one to do the estimate. And if it's alternating series, if it is alternating series, you can use either one to do the test. Is this clear? Okay, any questions at this point for this exam? Okay, perfect. Does this answer your question, Carl, as to Lagrange remainder estimate? Does this make clear?
Yeah, I think so.
You think so?
Yeah.
Okay, so yeah, if you have a function whose Taylor series is alternating series, then for the error estimate, you can use either the Lagrange remainder estimate or the alternating series test. Like in this case, sine x is actually given by an alternating series in this case. But if it's like e to the x or something else, which is not an alternating series, then the only thing you can do is actually by using the Lagrange remainder estimate, okay? And you should be able to know what is your functions and what is your n, what is your a, and what is the corresponding derivative you're looking at, which is always n plus 1's derivative. And you're looking for the maximum value of that function in between a certain range that's given by this a, okay? So that's the type of question you'll be asked. Generally, you'll be either giving alternating series and ask for error estimate by writing out the first few terms and looking for the next term as your error bound, or you'll be using the Lagrange remainder estimate for a given function by first computing the nth degree Taylor polynomial and then computing the remainder estimate by using this formula here. Okay, so that's a general type of question that will be asked for the final exam. Okay, so this is the first type of question we want to do, is by looking at the Lagrange alternating series estimate. Now let me do one question about the geometric series. I think this is something that you guys definitely already know very well, actually. So let me give a kind of let me see if this one makes sense. So let's look at a harder one, example 2. So summation n equals to 2 to infinity, 2 to the 2n over 24 to the n, okay? So for this one, what you want to do is, in order to find out, the original question is to find the numerical value of the given series. If you look at the question here, if on the exam you were asked to do something like finding the numerical value of a series, there's only 2 possibilities. You either have a geometric series or you have a telescoping series. Based on the form of the series here, it must be a geometric series. So there's no doubt you will be dealing with a geometric series and nothing else. And the right way to do this problem is by writing out explicitly what's the general formula for the nth term, which in this case can be written out very easily because this is 4 to the nth power in the numerator and the 24 to the nth power in the denominator, which further equals to n equals to 2 to infinity 1 over 6 to the nth power. So here I'm combining the numerator and denominator into one fraction and raise that to the nth power. The only subtlety here is that this is starting from n equals to 2 rather than n equals to 0 or 1 as you used to. So to use the summation formula, what's the very first term, initial term, is actually given by n equals to 2 corresponding term, which is 1 over 6 to the second power. This is your initial term, right? The very first term in your series. And what's the ratio in this case is 1 over 6, obviously, because this is n, right? If this is 2n, you have 1 over 36 or something like that. And this is the answer for the final exam. So this is the ratio. Of course, again, you'll be simplifying your answer on the exam and make it to a kind of a very reduced form. And that's the answer, okay? So I don't think this will be a major problem for you guys, actually. Okay. So that leaves us to the different convergence test technique. We have learned comparison test, comparison principle. We have learned integrator test. We have also learned about absolute convergence and the ratio test and root test. Let me remind you of the exam question that we are doing today on this last exam is the following one. The question, actually, there's one question asking you about finding if this one is converging or not. Okay. So how many of you actually get this one? You think you get this one correct? So what I'm trying to say here is there are two ways to solve the problem. The traditional way, that is using the ratio test that everyone's comfortable with. The other way is by using the root test, nth root test. I believe that Dr. Chadwick must have taught you guys this method too, but actually on the solution he sent out to us, he actually also used the ratio test. But let me see that if you use the root test, this question is actually very simple. What is the root test? The root test is by looking at the nth root of the an and looking at the limit of that. So in this case, it's actually limit when n goes to infinity. What is the nth root of an? So it's like 2 to the 2n over n to the 2m to the 1 over n, right? Which equals to limit when n goes to infinity 2n over n squared. And what is the answer for that? This equals to 0, right? Because the denominator is a degree 2 polynomial. It's quadratic. The numerator is linear. So linear is slower than quadratic in terms of growth when n goes to infinity. So the answer is 0. And this means that the series is converging here. That makes sense? Okay. You see that when you apply root test, how simple the answer is actually. But if you insist of using the ratio test, this is what you get. You get an plus 1 over an equals to 2n plus 2 over n plus 1 over 2n to the nth power times n over 2n over n plus 1 over 2n plus 2, roughly speaking. Okay, so actually this equals to 2n plus 2 to the nth power times 2n plus 2 times n to the 2n over 2n to the nth power times 1 over n plus 1 to the nth power times n plus 1 squared. Okay. For this problem, you should realize is that when you raise n to n plus 1, actually the denominator has this n plus 1 actually has one more term than an, actually one less term than an, actually, because the denominator I shouldn't see that actually. Yeah, because the denominator actually grows 2 more terms and the numerator only grows 1 more term. So there's an imbalance here, is that this is actually, you have a quadratic here, you have a linear here, everything else matches up to the degree, right? This is 2m, sorry. Okay. And then you realize you can do the following simplification, is that you have 1 plus 1 over n to the nth power times 2n plus 2 over n plus 1 squared times, this is going to be 1 plus 1 over n to the 2n over 1. Okay. But this actually equals to 2 over n plus 1. Let me write it more explicitly. So in this case, you can see that the limit of the expression when n goes to infinity, this part goes to e, whereas this part goes to 1 over e squared, right? You can recognize the familiar expression involved here. But this term goes to 0 because the reason I just mentioned. There's one more term in the denominator than in the numerator. They are of the same magnitude because they are all linear in n. But in the denominator, you have 2 copies of linear terms, which is quadratic. But in the numerator, you have only 1 to compete with that. So this term, actually, this competition, the denominator becomes larger and larger. So this whole thing becomes 0. Okay. So then everything goes to 0. That also tells you that it's converging there. Okay. And because the series itself is positive, so that means it's an absolute convergence series, right? So there's no other possibilities. So both way shows that it's converging absolutely as a positive series, but you can see how simple it is for the root test than using the ratio test. Let me remind you, this is probably the only one scenario you want to use the root test rather than using the ratio test, because you can see that they are both raised to the same order, which is linear in m. If it's not that case, you wouldn't want to do that. So still, the general approach would be using the ratio test. Only in these very special cases that the exponents are all linear functions of n, you want to do that. If you change the question into something like n factorial in the denominator, for example, it's 2n over n to the n factorial, or something similar where there's no n in the denominator or things like this in the exponent, you still go to the ratio test. Another reason is because you have this n factorial term. Okay, so there are different indications which method might be easier. So I'm just reminding you here that there are 2 possible tests you can apply to this kind of general form, to this kind of a series. Keep your mind alerted when it comes to the testing. Think about which test will be simpler for your question first before you dive into the solution. Does that make sense? Okay. So this is about the testing, and also there are comparison test and the integral test. I don't think I have enough time to actually go over an example like this, but I strongly encourage you guys to actually look at the previous questions have been reviewed so far. And yeah, really, I think comparison principle is something that's kind of conceptually hard to understand if you didn't do enough questions to really understand it. As for integral test, I mentioned several discussion section ago that there's only 1 or 2 specific questions you want to be careful about is whenever you have things like log n to some power, let's say p, over 1 over n or things like this kind of test series, you want to use the integral test. This is a very typical question where you want to use integral test because you realize this is the differential of f log x to the p's power. When you differentiate, you get 1 over n involved there. Okay. Okay, so this is for the testing, the approximation, and the summation of geometric series, and the different estimates. Okay. Another thing I haven't mentioned here is about the differentiation and the integration rules, and the integration of power series.
Bo, can you also go over how you would do the integral test there?
This one is just like, you know that log x to the p's power over x, integration of these from 1 to infinity is integration of 1 to infinity d log x to the p plus 1 over p plus 1 d, something like that. because you realize when you differentiate log x to the p plus 1 over p plus 1 with respect to x, you get log x to the p's power over x dx. But this one can be integrated.
But then what's the answer? What are you supposed to do?
Oh, if the integral is converging, that means the series is converging. If the integral is diverging, that means the series is diverging.
Okay, so you do what we did with the previous
Yeah.
chapter with improper integrals.
Yeah. Yeah. So basically, the kind of question involving the integral test is for the general formula is whenever the general formula of Fm that you are looking at is something that can be integrated easily by using integration by parts or integration by power rule or things like these. If this formula, this expression can be integrated easily, the integral test will be doable to the question. And the convergence or divergence situation of the series is governed by the corresponding integral you're looking at, an improper integration that you're looking at. That make sense?
Yeah, thank you.
Yeah, definitely go over a question on integral test and make sure you know this without any, you shouldn't have any blind spot at this point for the final exam. So definitely go over this kind of topics and do 2 to 3 corresponding questions from the textbook and reading the examples in the textbook to familiarize yourself with the corresponding kind of question. Okay. And also similarly, you want to do something for the differentiation and integration rules for power series. For example, you want to know how to find the tangent inverse, how to find the power series for tangent inverse x, how to find the corresponding power series for 1 over x, log 1 plus x, and things like these, which are very typical, and you can find them in the textbook. Okay. Learn about these, and also integration, for example, 1 to 0 to 1, 1 plus x squared dx, things like these. Okay, so I'm just making a list of questions you might want to look at for the final exam, actually. I mean, as a very simple baby model for the final exam. Okay. But understanding these baby cases are essential for the final exam because the more complicated situation are just built from these. Okay. Okay, so with that said, actually, let me dive into the part which I want to emphasize the most today is in different techniques of integrations. So first, we have integration by parts. For example, the corresponding question like this. And also we have trigonometry kind of questions like sine t, cosine t to the 5th, tangent x to the secant x to the 4th power maybe, dx, things like these, right? And also you have the partial fraction, which is integration maybe 1 over 2x squared minus 16x plus, actually this is not even, this is actually more a completion of square. This is completion of square. You can do all partial fraction as if you want also, okay? And also partial fraction type questions like x plus 4 over x plus 1 squared dx. Okay. Let me remind you in each case, how would you do that? So the integration of parts, there's no magic. You just have to realize. So first of all, what you want to use integration of parts is when you are given an integrand, which involves 2 distinctly different type of functions. For example, if you look at the list I'm making here, this 2 is a product, but it's a product of the same kind. These are all trigonometry functions. Similarly here, this is nothing but a fraction. This is still a fraction, right? So it's a fraction of 2 polynomials. So that's a reminder that you want to use partial fractions. But where in this case, you have polynomials times logarithm, so that's definitely going to be an integration of parts kind of question. The only thing that afterwards you have to think about is what's your u and what's your dv. And that's where the L'Hopital rule comes into the picture. You always make the ones in the list to be ahead of the list to be a u actually. In this case, for example, logarithm goes ahead before polynomial, so this will be your u, okay? And your dv will be x squared dx. Therefore, when you do integration of parts, the next time in the computation, the differentiation will be shifted to u, so that making this one into 1 over x, and hence everything becomes a polynomial type of thing. Okay, so that's how you do this kind of questions. So I won't be finishing this kind of question today, but because I can see from the participants here, I have total confidence in you guys here actually to do this correspondingly. But you definitely need to work on these, practice a little bit before the exam, so that you familiarize yourself about this. And also, my suggestion for the upper and lower bounds is that you always first finish the indefinite equation before you evaluate the answer. You only insert the value at the very last calculation. Okay, don't do it in the beginning, because that will mess up your computation a lot. Try to think about this as an indefinite integration first, and only in plugging values at very last step. Okay, but for trigonometry type of questions, there's no magic. You just have to know the different scenarios. If both are even, if both are odd, if someone is even, someone's odd, there are different situations in both cases. And also learn about the sporadic case, like integration of tangent x, integration of secant x, integration of tangent square, integration of secant square. Things like these will help a lot, because the kind of sporadic simple cases are the building block for more complex questions. Again, I think I have reviewed most of them actually in class, either before the spring break or after the spring break. So you better look into your notes and look into the textbook to remind yourself of all these. Okay. As to the third group, the partial fraction or completion of square, or maybe partial fraction here. So let me quickly see this. What this happening here is, you can always take out constants outside to make the polynomial with leading coefficient to be 1. That's crucial. If the leading coefficient is not 1, the very first step you want to do to a quadratic expression is to make it into a polynomial of leading coefficient 1 by dividing that. As you can see from this case, you have x squared minus 8x plus 20 then. So when you do a completion of square, you should realize this actually equals to x minus 4 squared. But because it's minus 4 squared, so you are left over with a 4, which is a positive thing.
Can you move the paper up, please?
Oh, sorry. Yeah. Can you see that now? Okay.
Thank you.
Yep. So that means you are having something like a squared plus 4, or a squared plus 1, if you really think about it as this as a constant. So it's x squared plus a squared type. So that is a reminder that you have an arctangent type of integration. Does it make sense? Okay, so again, let me rephrase. When you have a quadratic whose leading coefficient is not 1, make it to be 1 first before you do anything else. Once you have done that, then completing square to see if you can do the completion of square like that. Another approach will be finding the factorization of these. But due to the fact that this one is something squared plus 4, you won't be able to find a factorization for these. And that's general hint to you that it's going to be arctangent 2. Okay, so that's two different heuristics you should have is, whenever you see quadratic, always try to find, after you do dividing the leading coefficients, you always first try to find factorization to it. If you couldn't find factorization, there's only one possibility. It's going to be something squared plus something positive, because in this case, there's no solution to the polynomial then. And that's why you cannot factorize it. And hence, you will be having an arctangent type. If there's no such a 4 here, you'll be having something similar to the question I wrote over on the right-hand side, which involves partial fractions here. If you can find a factorization with different solutions, then you can go to partial fractions again. And that's a general scheme for solving integrations involving a quadratic in it. So let's now look at the right-hand side, this example here. So after you do this, I won't be writing out the answer further, but you should be able to find out this actually is an arctangent by using the correct substitution here. Also, yeah, so this is u squared plus 2 squared, right? So the A in this case is 2, and then you have the formula for arctangent like x over 2, I guess. So that's the kind of question, the answer you have. And don't forget the constant c afterwards, and also you have this constant 1/2 in front. Okay, so once we have done that, then the question is when you have x plus 4 over x plus 1 squared. In this case, the denominator is actually of a quadratic, which has a repeated linear term. So the corresponding idea for that is no longer this is no longer going to be arctangent or sine, arcsine type of thing. So there are two different approaches for attacking this, but the simplest one is to using the partial fraction. In the case where you have repeated terms, in linear terms in a denominator, then the corresponding template will be something like this. I hope you guys all remember these. How do you write out the right templates for partial fractions? And also because the denominators here, the reason why I do not need to do any long division is because the degree of the numerator is smaller than the degree of the denominator, which if you have a degree 2 polynomial in the denominator, you will have to do the long division first and then perform the partial fraction to the remainder terms, meaning the real fraction part. Okay. Does it make sense how you should be approaching this? Okay. And after this, you solve for A and B by equating both sides and using different techniques. One possibility is by looking at the coefficients of the polynomials and let them be equal and solve the system of equations. Another way is by plugging values. In this case, I believe that x equals to -1 will be a good choice for plugging values into the expression here. Okay. So with that said, I guess that's all for the integration techniques. Okay. So let's now look at the list I have here. The other thing I want to say is that is about the inverse function here. If you look at the list we have here, for inverse function theorem, essentially that you have to be able to recognize if a function has the inverse or not by looking at its derivative being positive, constantly positive or negative, or somewhere positive, somewhere negative. I think that this part I have done enough exercise in class during the first half of the semester actually. So I'm not quite worried about these actually. L'Hopital's rule, always check if the fraction is an indefinite form before you differentiate the numerator and denominator. Okay, make sure it's a 0 over 0 or infinity over infinity type before you use it. And that's the thing. And also be careful with the change of base kind of argument. For example, when you have something like this, when x goes to 0, you take the e to the something, make it into the exponential form. That's what I'm talking about. Okay. That is everything before the first 5 atoms. And as to number 6, I guess there's no way for me to review all possible questions. But let me see some of the major types you want to actually look at. Is the following thing: is so far the tanks are of the following given forms. Because the final exam will be an open textbook one, so you should be expecting a question that is generally harder than the one you have encountered for the previous 2 exams. Okay, so that means the shape of the tank will be maybe hard to solve in some. It's not going to be a very standard one, but at least you should know the basic models. Okay, these are the basic model. When you have a half cylinder lying horizontally, when you have a cone, when you have a hemisphere, and when you have a cylinder. And also the other case is when you have y equals to fx revolving around a given y-axis. For example, the function may be given by something like y equals to x cubed, things like these, and revolving it around the y-axis and producing a surface of revolution, and use that as a tank. Okay, so these are the major types of questions, and I think that for that part, you really need to do it, review for yourself, case by case. How would you do that? For example, whenever you have a horizontal, whenever your slice, vertical slice, I mean this direction is a cylinder, is related to the circle. For example, in number 1 and number 3, when you cut it vertically along the x-axis, you see in this case you have both a hemicircle, and that's where you are going to use Pythagorean theorem. Okay. But if you cut the cone in the middle, vertically speaking, you get the triangle there, and that means you're going to use similarity of triangles. The cylinder is very simple. I won't be saying anything. The last case is where you have a function y equals to fx. You always find a relation between the radius r, which is x, in terms of a height, which is y equals to fx. So you need to invert the function to find the height in terms of x in some sense. Okay, imagine that you are integrating in the y direction. So that means you want to find the function of x. You want to write x as a function of y. That's what I'm saying. Find the inverse function to it. And that's the reason why we learn inverse function, because in practical life, there are many scenarios. You are given a function where, for example, you're expressing the relation between the temperature to the humidity. Maybe you can find a function inverting the relation there. That's actually what you really need for that. Okay, so this is actually for the tank problem and also for the work problem. You have to do with that. For the volume problem, I don't think, has Dr. Chadwick mentioned something about revolving around the different axes of rotation? For example, revolving around x equals to 5 or y equals to 3. Has he mentioned anything about that?
Not really.
Not really. Okay, then you don't have to worry about rotating around different axes. Focus on the revolving around the x-axis and the y-axis cases where you have either the disk method or the cylindrical method or washer's method. And also the shells method is about revolving around the y-axis. Okay. So make sure you review all these, and there's no other way you can do a good job except practice on each type of question I listed here, at least 3 to 4 model questions. I mean, before you can call. So test yourself on the list of topics by looking into the corresponding question in the textbook, and especially look at those kind of similarly tricky questions, because again, let me see that the final exam will be an open textbook exam. Generally speaking, the open textbook exam will be harder. So you should be knowing more complex questions than just basic model questions that you can solve. Okay. As to good resources for reviewing, I would say TestBank is still a #1 place to looking for practice questions. Unfortunately, they don't have a solution to it. But let me say that again, 2018 fall exam is a reasonable hard exam, but with also the solutions given there. And
which one?
2018 fall. Yeah, this is the only one I know where they actually have a solution to it on accompanied. Another thing I want to say is that work together. I mean, for example, most of you know some of your fellow students already from this semester. I strongly encourage you guys to form a small study group on Zoom to discuss with each other. Actually, check each other. If all of you know a given topic from bottom to top to the thorough details, you can solve this problem. Okay, you can actually find maybe some kind of exam together and solve them together, and as a practice exam, you know, and then checking answers to each other afterwards as a good exercise. Okay. finally, I want to say that I really appreciate you guys for being here every time. You guys are the reason why I love teaching, actually. To be honest, I really like you guys, actually. So I wish the best for you guys for the final exam and also for your future study in Maryland, also to your career. And I strongly trust you guys will have a very bright future, actually. And thanks, Emily, Brian, Justin, Carl, and Pat. I wish the best to you guys, actually. Okay, so good luck on the final. If you have any questions, feel free to email me anytime you have. And let's all work to the end of the to the final. Okay. And if you want to discuss with me your grades, email me. Let's arrange for time to do that. Okay.
Bo,
Yep.
thank you so much, man. You were awesome. I was having technical difficulties one day when I sat in on your discussion, so I sat in on another TA's,
Uh-huh.
and it wasn't even close. You're
Oh.
the best, man. Seriously, so great. All
Thank you for
semester,
saying
all
that,
year.
actually. Thank you for saying that. Actually.
It's true, man. No, you so much better. You condense it into a profound way, and this semester has been incredible because of you.
But
So thank you.
I want to thank you because I mean, without you trying to push me to learn this, I won't be saying the thing that's you know what I mean. This is an interaction that needs both parties to be really involved, and I really feel sorry that we have this kind of pandemic and everything's crazy. We cannot actually sit down in classroom and see each other face to face, which will be a much better approach to learn mathematics. But unfortunately, yeah, this is the way. Hopefully next semester, I mean, you guys will be back on campus and we can say hi to each other maybe somewhere. But I don't know. I mean, at this point, it doesn't seem very optimistic. But yeah, but still, safety and health is the first priority you guys should be considering for your family and for yourself, actually. Okay, so let's keep working hard. Yes, yes. Okay, good luck, you guys.
All right, have a good one.
You too. Bye.